So this is sections 11.1 and 2, part A. And this is the second part of the video. We've been looking at vectors and what they look like in terms of a notation when we put them in standard position. We now would like to look at what we mean by the magnitude of a vector. Remember that vectors were supposed to have two properties. They indicate both size and direction. It's the size of the vector that we refer to when we talk about its magnitude. The size of the vector, geometrically, is shown as the length of that vector. And again, we refer to it as the magnitude. So any of those words. What's the size of the vector? What's the length of the vector? What's the magnitude of the vector? You're really being asked the same question, three different ways. All right, so how do we find the magnitude of a vector? First of all, make sure your vector is in standard position. Really important. If your vector is in standard position, then the magnitude for v, which we write this way, notice it just looks like absolute value bars, but for vectors we read that as the magnitude of v, or the length of vector v, can be calculated as the square root of v1 squared plus v2 squared plus v3 squared. If you only had a two-dimensional vector, of course, there wouldn't be any v3. In fact, speaking of two-dimensional vectors, this is actually just a version of a very, very famous theorem or formula. If I look at the two-dimensional case, standard position vector, so I started it at the origin, and if this is my terminal point, so my vector is v1, v2, then notice that the length of that vector, the magnitude of v, is simply the hypotenuse of a triangle. The x component, v1, is the x value, the y component, v2, and then we just have really a Pythagorean theorem going on here. v1 squared plus v2 squared is equal to this length, the magnitude of v, squared. Or if I take the square root on both sides, we see that our magnitude of v is just the square root of v1 squared plus v2 squared. Here it is in 3 dimensions, so really this is just a 3-dimensional version of the Pythagorean theorem. You can see it really easily with the 2-dimensional version. All right, let's find the magnitude of a couple of vectors. The first one is given to us in standard position. I know that because of the angle brackets, so I can just go ahead and use my formula. This would be the magnitude of the vector c is the square root of -3 squared plus 5 squared plus 2 squared. What is that? 25, 29, and now let me write it out so I don't make another arithmetic mistake here. Let's see, 38. And so this vector has a magnitude or length of the square root of 38. What about the magnitude of this vector shown in the graph? This is not in standard position, so I'm going to start by rewriting it in standard position. The initial point right now is 1, -2. Looks like the terminal point right now is 5, 4. So the vector A, if I take terminal minus initial, again, this is the terminal point, this is the initial point. And so in standard position, I'd have 5 minus 1, or 4, and 4 minus -2 would be 6. Now that I've got standard position, I can use my magnitude formula to get the magnitude of A. The square root of 4 squared plus 6 squared. Let's see, 36 and 16 would be 52. Or if I simplify my radical, 2 times the square root of 13. By the way, I don't care so much about simplifying radicals. If you miss one, don't worry about it. I'm not going to jump all over you for that one. All right, so finding a magnitude. Be sure you have standard form. And once you do, it's just the square root of the sum of the squares of the components. All right, so that's magnitude. All vectors have both magnitude and direction. So now that we've talked about magnitude, let's talk for a moment about direction. How do you find the direction? And we are going to talk specifically right now about a two-dimensional vector. Three-dimensional ones for direction are much more complex, and we'll come back and mention that in a moment, but mostly we're going to be talking about the two-dimensional ones. If again our vector v1, v2 is in standard position, really important that we have it in standard position, then the angle between the vector and the x-axis satisfies the equation tangent theta equals v2 over v1. We may still need to think about the geometry to make sure we get our theta in the correct quadrant, but this formula will get us 90% of the way there. Okay. First of all, let's just talk about this equation and where it came from. It's really just basic trig. If I again say, hey, this is in standard position, so it starts at the origin, and it's the vector v1, v2. If I draw that same triangle I did last time, so my x value would be the v1, and my y value would be the v2, then theta, the angle between the vector and the x-axis, I could write tangent theta is equal to opposite over adjacent, or tangent theta would equal v2 over v1. So that equation there is nothing more than standard trigonometry. All right, let's talk about writing directions for a couple of two-dimensional vectors. Far away from me here. All right. My first vector, w, is negative 3, 3. So it looks like that. Standard position. Even though I think we can probably just look at that and see what our angle is, I'd like to go through the process just to show you what can happen. So I would start out by saying the tangent of theta is, in this case, maybe I would say w2 over w1, 3 over negative 3. So the tangent of theta is negative 1. Now, this is one that we can just either know or look up on a unit circle, but I want to point out to you that if I were to actually do this on a graphing device like a calculator here, right now I'm in radian mode. Let's just go to degree mode. And if I were to take the inverse tangent of negative 1, it's going to give me negative 45 degrees. This is what I mean by making sure you're situated in the correct quadrant. Now, of course, we know that negative 45 degrees really would have been down here. So that's not the one we wanted. We wanted the one up here, the supplement of the 45-degree angle, or 135 degrees. So to answer this question correctly, one option would be to say, to describe the direction, theta is 135 degrees. When you give me a value of theta, it's always assumed to be the angle with the positive x-axis, every single time. So make sure you're always giving me the angle with the positive x-axis. That is one perfectly correct way to answer that question. Now, the directions, though, said answer in two different ways. The other way is the north, south, east, west. So I could describe this vector in a couple of ways, actually, using north, south, east, and west. This is north, and this is west. So I could say, for example, this is 45 degrees west of north, or for that matter, 45 degrees north of west. So the second way to describe direction is to use the north, south, east, and west. All right, let's do something similar for the second one. Our vector here is -6, -4. So it's in quadrant 3. And I'm going to start out by saying, to describe direction, tangent theta, V2 over V1 would be -4 over -6, or 2/3. That means to get theta, I'm going to take the inverse tangent of 2/3. And I'll just do that on the calculator. Again, right now it's set in degree mode. And I get about 33.7 degrees. Now, once again, it's clear to me that this is not in the correct quadrant. 33.7 would be the one over here instead, right? I want this one. So that's a full 180 plus the 33.7, which would give me what? 213.7? So one option would be to answer theta equals 213.7. Again, if I'm just going to answer with a theta, I always have to make sure that I'm giving the angle with the positive x-axis. Alternatively, I could answer with the north, south, east, and west. Let's see, this is west, down here is south. So I could say, let's see, if that's 33.7, that means this here is 33.7. I could say that we are 33.7 degrees south of due west. Of course, if I wanted to calculate it, I could subtract from 90 and get that angle and say that was west of south, but one sort of north, south, east, west description is sufficient. All right, particularly in application problems, we tend to like to use the north, south, east, and west. They make sense to people in sort of everyday life. That brings us to the end of 11.1 and 2, Part A.